Meeting the Challenge, Geological Disposal of UK High Activity Radioactive Waste. My name is David Shilston. I'm President of the Society, and it's my special pleasure to introduce today's speaker, Professor Rebecca Lunn of the University of Strathclyde. The UK has substantial volumes of so-called legacy wastes, arising from its weapons programme, from its various experimental reactor programmes, from nuclear power plants, and from the reprocessing of spent fuel. This lecture will discuss the technical and societal challenges that must be overcome for successful construction of a geological disposal facility for these wastes in the UK. Our speaker this afternoon, Rebecca Lunn, is Professor of Engineering Geosciences and Head of the Department of Civil and Environmental Engineering at the University of Strathclyde. She has over 20 years research experience in hydrogeology, with particular focus on energy. In 2011, she was the first woman and the first engineer to be awarded this Society's Aberconwy Medal. And, stop press, Rebecca has just become the first civil engineer to be elected as a Fellow of the Royal Society of Edinburgh. Oh, first female Fellow, I do apologise, the first female Fellow. Ladies and gentlemen, please welcome Professor Rebecca Lunn.
Okay, good afternoon. Welcome to everybody. Thank you very much for inviting me to give this lecture. Hopefully you will find it interesting. So I'm going to discuss the challenges that we face at the moment in constructing a geological disposal facility in the UK for higher activity wastes. Because of what I'm wearing, I'm not carrying a mic, so please tell me if I wander away from the podium, because I'm not supposed to. So you won't bother hear me. Okay, so before we talk about waste, I want to say a little bit about power. I think it's not appropriate to talk about waste without thinking about the context in which they're generated. So this graph at the bottom here shows the electricity supplied by fuel type from 1980 to 2011 in the UK. It's from the Department of Energy and Climate Change. And you can see that nuclear is the big purple bar in the graph. In 2011, nuclear constituted 18% of the UK's electricity supply. The big growing one here, the green one, is gas supplies, and the diminishing blue is coal. So nuclear formed a very important part of our electricity generation over the last 30 years, and will continue to do so for the near future. And we also need to think about what we use energy for. So these are data just from 2010 to the middle of 2013. And you can see that we have transport at the bottom, which is predominantly hydrocarbons. And then above that, we have mostly electrical use, so industry, services, and domestic energy supplies. And you can see that they go up and down annually, which is with heating requirements for the winter. So this is our energy production, and the important thing to think about is that this is baseload energy production. So there are two types of energy production. Baseload is the energy that we require to keep ourselves going in a normal type, that we must be able to rely on in normal times. So reliable energy production is oil and gas, nuclear, biofuels. You can use geothermal energy as baseload, hydropower because you have storage in a reservoir, so you can release at a constant rate, and tidal. What you can't use for baseload energy is wind and solar. So hydropower I've got twice here because you can also use it for peak. So wind and solar, because the source of the energy relies on it being windy or not cloudy, you can't use it reliably all the time. So you can't use it at the moment for baseload energy production. So it will contribute when we have a large peak demand. For example, when we're all watching final of X Factor before Christmas, where energy peaked hugely, actually. So there are, unless we solve our energy storage problem, it's not an option at the moment. Unless we have big batteries, it's not an option at the moment to use renewables for baseload energy. Okay, nuclear power. Advantages of nuclear power: it doesn't depend on fossil fuels, and it's not affected by the fluctuating oil and gas prices. And it has the advantage that if we can meet our energy requirements through nuclear, we're not reliant on foreign energy imports. The disadvantage of foreign energy imports are obviously political, in that we rely on other countries for our base load energy capability. And the previous legacy nuclear has estimates for the worldwide estimate from the Nuclear Energy Institute is that 2 billion metric tons of CO2 per year has been saved by not generating that electricity or using fossil fuels. However, there are disadvantages, and that's what we're going to talk about here. And the big disadvantage is that the current technology that's being used, and I'm not saying this is necessarily true of the future technologies that are being worked on, but the current technology produces nuclear waste that has to be managed over very long timescales, tens of thousands to millions of years. So we need to make some tough decisions. We need to meet our baseload energy demand if we want to keep our economy going, and we need to meet targets for greenhouse gas emissions. We can do things through carbon capture and storage technologies, but at the moment they're very immature. There's no industrial scale carbon capture and storage technology, so it's not a proven technology. And if we want to use renewables, we need a solution for energy storage. So I think that gives a sort of context for the current need for nuclear power. So to come to what we were going to talk about here, what's radioactive waste? So I said that the disadvantage of nuclear power is that you generate radioactive waste. These are the definitions that come from the NDA's inventory, which is a public document. Low-level waste is, in the UK, it's mostly building rubble, soil and steel. And so you have three types of waste: low-level, intermediate level and high-level. Low-level waste, mostly building rubble. Intermediate level waste are things like nuclear fuel casing, sludges from the treatment of radioactive liquids, and there's graphite within the reactor cores that constitute intermediate level waste. And then when you come to the high level waste, what defines a waste as being high level is that it's heat generating. And these are generally derived from reprocessing of nuclear fuel. So it's hot, it's active if it's high level waste. So how much do we actually have that we need to dispose of? So these are data from the 2013 NDA waste inventory, and they're based on estimates from the existing nuclear power fleet. So we have 4.5 million cubic meters, which is of waste. And to give you some idea of how, that's a very large number, to give you some idea of how much that actually is, it's around 4 times the volume of Wembley Stadium. So if you filled Wembley Stadium up to the top, 4 of those is what we need to dispose of. Most wastes are stored at existing nuclear facilities. So most of them are stored at Sellafield. And we have also, what's not included in that figure, is any waste that may come from new build nuclear power. So that's something to consider into the future as well. So if we look at what we have here in the inventory, the light green segment here, the bulk of it is from spent fuel reprocessing and nuclear power reactors. And then we have some small parts from other industries. So there's energy research, and the medical industry uses nuclear technology for imaging and also for things like radiotherapy for cancer treatment. Defense industry, and then we also have waste from fuel fabrication. So on the right-hand side, you can see what a modern store looks like. Not all wastes are currently in this kind of store. That's what we're working towards. But this is the intermediate level waste store at Hunterston A. So this is a modern facility. You can see the idea of waste being stacked. And this is a high-level waste store here with vitrified waste in it. So each of these little bits on the ground contains packaged waste. So what do we do with it? So in 2003, the UK set up an independent committee for radioactive waste management to make to advise government ministers on what should be done with radioactive waste. There are a lot of different methods in the available that people have suggested, and they set up an independent committee to review them all. And the committee contained non-technical experts, so they were well-educated non-technical experts, so not scientists and engineers. The committee conducted an extremely extensive public consultation exercise, I think probably the most extensive that's been done in the UK, and that included things like having citizens' panels throughout the time that the committee was there, which were revisited periodically and given more and more information, and the decisions those panels made and the thoughts they came up with contributed to the final recommendations. And at the end of it, they recommended that geological disposal was really the only proven technology at the moment, and that also that we had a moral obligation to deal with our wastes for future generations. So they made recommendations to government, and government accepted Quorum's recommendations and produced a white paper in 2008 called Managing Radioactive Waste Safely, a framework for implementing geological disposal. It came out in June 2008. And as part of that new process, the Quorum Committee was reconstituted. It was completely reappointed as an expert technical committee instead, with a very wide range of expertise. And it had a new function, which was independent scrutiny and advice to ministers. And just, it's not really relevant to this talk, but for information, I joined Quorum in 2009. Okay, so what is geological disposal? Geological disposal, if you look it up on Wikipedia, there's a nice definition, which is up here, and it's a nuclear waste repository. A nuclear waste repository is an engineered facility that's deep below the ground, and the important thing here is that it's engineered. So it's carefully constructed, and it uses the waste form itself. So the design is in how the waste is held, the waste package, engineered barriers are put in it, and it also relies on the geology. So it relies on a number of things to generate safety, with the idea, with the result that you provide a very high level of long-term isolation and containment that doesn't require any future maintenance. If you've got long-lived waste for 10,000 to a million years, the concept that you can pass information over hundreds of thousands of generations about how you should store and manage that waste is not really plausible. It needs to be an unmanaged system for disposal so that you can leave it safely. So in the UK, deep in the white paper is defined as being 200 to 1,000 metres below the ground surface. And this here is a Swedish example of the Swedish waste canister. It's a copper container, and inside it you've got the fuel rods. Okay, so who's done what? So there's been a lot of activity on developing this technology throughout the world. At the moment, you've got 13 countries, as far as I could count, that are currently pursuing geological disposal. So it is the only disposal option that's being pursued. So, and they're pursuing it for a variety of different waste types. So 4 sites are now in operation. This is one of them, the WIP site in the US. 3 sites under construction. 2 sites, they have submitted a license application for it. So the safety case is completed, the license application has gone in, and they're waiting on a decision for where they can construct. And there are a number of other sites for which safety cases are being developed, so that are in discussion. So moving forward on a site for geological disposal depends fundamentally on a safety case. So what a company that wants to develop a geological disposal facility is looking to do is to develop a safety case. A safety case is a formal compilation of evidence, analyses and arguments that quantify and substantiate a claim that the repository would be safe. And that's the international definition from the Nuclear Energy Authority in 2013. So it's rooms full of paperwork and years of site investigation and scientific expertise, modelling and prediction. There's a huge amount of work has gone into developing safety cases for the current sites and the ones that are moving forward. A safety case develops with time. So early safety cases are made during site characterisation, so when you're first looking at a site, and they contain very general assumptions about host rock geology, what engineered barriers might be, the layout of the repository. They're a general idea. As site investigation continues and you develop more and more knowledge over many years, that early safety case becomes something much more specific and becomes very data driven. And in the end, you're looking to have sufficient factual detail to provide confidence for a regulator that the repository will be safe into the future, and that over the lifespan of the waste, there will be no harm, no risk to the population. So as I said, the safety case isn't assessed by government, it's assessed by the regulators, and the regulators, or the company, and the regulators are independent. That's true of all nations. A company will build, or government will build the safety case. That case is then submitted to independent regulators. In the UK, those regulators are the Environment Agency and the Office for Nuclear Regulation. It has two parts, and I'm only really going to talk about the first part of it, so which is the one that most people can get concerned about. So the post-closure safety case is the safety case, is the case for it being safe once you close the repository. So it's the forward-looking case, predicting what will happen to your waste over the next million years and why you can guarantee that the public will be safe. There is, as with any other nuclear facility, a construction and operational safety case that will also go with that, but I'm not going to discuss it. Okay, so I wanted to give one or two examples to show that safety cases differ quite a lot. And the ones that have been developed in different countries are in different rock types, and the different elements of the safety case differ. So, and the role of the different bits in it differ. So first of all, we'll look at the one in Sweden. So there's a case that's just at the license application stage in Sweden, and it's actually the same concept, same safety concept, that's being constructed now in Finland. So it's past the license application stage. It's called the safety concept is called KBS3. Don't know what it stands for, and it's in a fractured granodiorite actually, but a type of granite. So probably mostly geologists, but for those that are not, a kind of hard black crystalline rock that you might get in your kitchen work surface. So you do see them polished nicely, and if you go to Aberdeen, most of the buildings are made from them. So it's hard crystalline rock where really any flow within the rock, any water or any option for transport is within fractures in it rather than the rock matrix itself. So the way that KBS3 has been constructed is what's called a multi-barrier approach. So you have this end, this is the cladding and the fuel assembly, so this goes in here. You have lots within the fuel assembly, and then the entire thing goes into a ductile iron insert, which is what you saw in the photograph earlier, and a copper canister, again, which is what was in the earlier photograph. So this here then is your waste container. So it's a thick copper canister. The copper canister sits within bentonite. So bentonite is a type of clay. It's quite a specific type of clay. Bentonite is a highly swelling clay. So it's very, very low permeability, and when you add water to it, it swells hugely. Its volume changes massively, and that means that it creates like a tight seal between the canister and the rock. So it swells out to fill all the gaps between the canister and the rock as it wets underground. And the way this works is that you put the canister in and then you fill up the engineered barrier around it. It's precision engineering. The engineering has a tolerance of around 1 millimetre between the bentonite rings and the canister, and they are rings like a flattened donut. So you stack up the rings like a child's stacking toy. So you stack up the bentonite rings and surround the canister, and these are in the deposition shafts here, and then these are accessed from a main tunnel, and that's backfilled with bentonite to stop any transport to make sure you inhibit any transport of radionuclides through the tunnel system. And then the whole thing is in an underground repository, which is, in the Swedish case, about 0.5 kilometre below the ground surface, so it's very deep. And you can see here that it's quite close to the coast in Sweden. So, what's the safety concept? So the KBS3 repository is for spent nuclear fuel, with a safety criteria of a risk of harmful effects being less than a 1 in a million chance over the whole time frame into the future. And its safety actually doesn't rely on timescales for water flow through the rocks at all. It relies on ensuring that radionuclides are not released at all from the waste canisters over the first million years. So what their safety is relying on, in fact, is that they have very low flow rates and that they can keep stable reducing groundwater chemistries at repository depth so that they get no chemical breakdown of the bentonite. So they don't erode chemically or physically the bentonite barrier. And the bentonite, which if you remember is the clay barrier, is what surrounds the canister. So the bentonite is used to protect the canister from oxygenated water so that you don't have copper corrosion. And it's also used to protect the canisters from any mechanical effects that you could possibly get from future earthquakes. The bentonite's not very rigid, it's quite plastic when it's wet, and therefore it damps any shock wave that could potentially come through the rocks from an earthquake and diverts it around the canisters. So so those are the two possible release mechanisms for getting waste out of the canister, and that's what it's there to protect from. So the safety case itself doesn't rely on transport times at all. In fact, in the case, they're assumed to be instantaneous if you get leakage. Okay, so this is the WIP site, which is completely different. It's in the US, and it's been operating since 1999, and it's in salt rocks. And actually, they're I think it's about 97% sodium chloride. It's very high salt content, and it's a thick salt layer. So this is for transuranic wastes, which are things that are like gloves and operational stuff that's been contaminated with uranium and plutonium. And the safety criteria for this is 10,000 years of radionuclide containment from the site. And the way this case works is different. So this case works because salt itself in the ground creeps. So salt flows as a rock, it's not static, and it flows into any holes and cracks. So what actually happens is that when you leave this vault, the salt will come in around it and enclose the wastes. It also means that in the salt rock that surrounds, there are no holes for water to flow in because they all shut up because the salt creeps from the weight above and it moves and fills all the holes. So the salt is dry, there are no holes in it, but also if you introduce any water, say from the atmosphere in here, because you're working in it and it might be a bit humid, actually that water will get sucked out as well and incorporated into the salt. And just to give you an example, mobile phones, I don't know if you've done this, but if you drop your mobile phone down the toilet or put it in a sink, same with your car keys, don't switch it on because you'll short-circuit it. Stick it in salt, you put it under salt, leave it there for a couple of weeks, take it out and the moisture will have gone and it will work, and so will your keys. You can do the same with rice, actually, if you're worried about salt corrosion. So you can do the same with rice. It works in a similar way, but it dehydrates the atmosphere. So the idea is that water can't flow, and then because of that, when waste is released, there's no way for it to travel. Okay, and the final one I'm going to give you an example of is in France. You have clay rocks. This is the French are they're in the process of developing a safety case for high-level and intermediate-level long-lived wastes in clay rocks. And they have a criteria from their website that the waste must represent no increased risk for human beings and the environment during the period of decay, so over very long timescales. And this does rely on travel time. So in this case, you surround it with clay rocks. The clay rocks are extremely impermeable, and very, very impermeable. So the time for water to migrate through the clay is actually doesn't flow at all. It just depends on mixing of the particles. It just depends on diffusion. So it just depends on random motion of particles. So the clay rock, the times are very slow, and also they've shown that in experiments in their underground rock lab, which is at Bua, has shown that the fractures that you do get, so when they tunnel, you get fractures for a metre or so on either side of the tunnel, just close up and heal. So the clay is slightly plastic still. The weight of the rock above means that the fractures heal and don't stay open. So within the clay, you also emplace the waste and disposal cells in their concept. So you have a waste package, and then that package goes directly within the clay. What's quite interesting about this as well is that these results actually are in keeping with results for shale gas. So in shale gas, the reason that you have to frack the rock to get methane out of it is because it is so impermeable, so things don't flow in it very well, so you need to crack it to get anything. But also, interestingly, you can't frack anything with a high clay content. So a clay content that would be high enough to use for radioactive waste disposal so that your fractures all heal isn't suitable for shale gas because you can't keep them open. So for exactly the same reason it's not suitable, so they're looking for things with shales with low clay content. Right, so what is the process in the UK? So there has been a siting process since 2008, and it relies on volunteer communities, which was recommended by Quorum, mostly because international experience has shown that siting, the biggest reason for siting failing is not having public support. So it was felt there was a need to have volunteer communities, and the process for that is that communities first expressed an interest. Then there was a long local consultation process, and then a formal decision in the community about whether to participate or not. Associated with that was a community benefits package, so a package to fund engagement with the community, but then a further package, a benefits package to a community if they hosted a repository that would include things potentially like improved transport, health facilities, wasn't defined. And importantly as well, data wouldn't be gathered until after the point at which community decided to participate. So there was a process that ran from 2009 to 2013. Unfortunately, only Cumbria County Council and 2 district councils within Cumbria expressed an interest in the programme. There was an extensive public consultation through having a siting partnership with members from the council, from the parishes, from the churches, and that resulted, at the end of that consultation process, a Mori poll was held that did show net support within all 3 regions. In fact, very high support in Copeland, but even across the whole county, there was more than just over 50% support to go ahead and decide to participate. But the decision was made at a council level, and what actually happened is that Copeland District Council voted to participate, Allerdale postponed their vote, and Cumbria County Council, the councillors voted against, with the result that the siting process the process we had didn't deliver as a UK site. And it's not whether it delivered it in Cumbria, it's just whether we delivered something at all with this policy. So with the result that we now didn't move forward with the one expression of interest that we had. So one of the reasons for that, I think, was that there was an extremely effective campaign, local campaign and national campaign, but mostly local campaign actually against the siting process in Copeland. And I just want to very briefly run through a little bit of the things that the campaign claimed. So this is the first of the claims that's on geology, that somehow we already knew that the geology, or that government or the implementer already knew that geology was unsuitable. This is from David Smythe's website, who's one of the prominent geologists. So there were 2 geologists presenting evidence for the campaigners against. And they presented this, which is one of the main arguments, that somehow water would flow down at depth and most alarmingly flow through your waste repository site and out before you hit the sea, just to notice here that this blue here is sky, not sea, and this white is sea, slightly confusingly, but this is his figure, not mine. So, and this is very misleading and simplistic, and I'm going to point out a couple of places where it's wrong. So for starters, as most of the geologists I'm sure will know, there's a very large fault, old fault, that runs along the side of that bounds the Lake District. So you have the mountains on the east side of Cumbria, and you have sort of lowland sediments on the west side, and between the two is a very ancient fault that's very large. And faults are well known to divert flow. At the very least, they'll divert it and have some kind of cracking along the side that will tend to channel it, but most likely they'll just be a complete barrier to flow. And in fact, it's the faults are one of the key reasons that you trap hydrocarbons for oil and gas production, because they form side boundaries to reservoirs. So it's well known that faults can form barriers, and this fault runs all the way up north to south. So you won't get this. Whatever else happens, that's not going to happen. Okay, also, if you drill down, I'm an engineer, you drill boreholes, if you drill a hole down into the ground, below a certain depth, the groundwater is salty. If you go deep enough, it's generally extremely salty, much saltier than seawater. Now, I'm sure that you've all made salad dressing. So if you make oil and vinegar salad dressing and you shake it up in a jar and you leave it, it settles out, and the lighter oil, the less dense one, floats on top of the vinegar, doesn't it? So you have balsamic vinegar or something at the bottom and oil on top, and it doesn't mix and it forms a nice stripy thing in your jar. So exactly the same thing happens with less dense fresh water on top of more dense saline water. So you have a salty interface. It's approximately 350 metres depth, in fact, in Cumbria, but and above that, the fresh water will float on top of it. So this acts almost like a barrier, and you will tend to get horizontal fresh water above that interface. You'll also see that there's a very alarming vertical exaggeration on this diagram. So this is in fact about 17 kilometres, this distance from the highest peak in the lakes to the sea, whereas this is just 1. In order to make it look more alarming, presumably. And you need a force to make water flow. It doesn't just choose to do it on its own. If you think about a swimming pool, the water doesn't flow anywhere because there's no driving force. You need a what's called a hydraulic gradient. You need a difference in water levels to make water flow. Now, if this is like a swimming pool, all the rocks beneath the water table, just a few metres below your feet, all of the rocks will be full of water. There's no gaps anywhere in the vertical. So what will actually, so this just, if you don't have a driving gradient, this just sits and goes nowhere, all of it. So there's no reason for this to go diving down below sea level at all. And finally, for a geologist, it's interesting that this picture has no geology on it. So his original picture is just all yellow, but in fact, there are layers of sediments here on the west coast, and some of them are permeable sandstones, and some of them are quite impermeable mudstones. There's some conglomerates as well. And the fact that you have layers of permeable geology will promote water travelling along the layer. It's much easier to travel along the sandstone if you've got some force driving you than it is to go through something that's impermeable. So whichever way you look at it, this diagram isn't going to happen. Okay, there are a few other claims that were effective. That community benefits for a bribe, you can take them away, but community benefits are standard in planning applications, not just for a geological disposal facility, for many other industrial planning applications. So, and also that governments always plan to return to the site. It just happened to be the only volunteer. So on a more national basis, I think that the driving factor actually against the disposal facility was an anti-new build nuclear power feeling. And embedded in all of this, I think, is a real prejudice from local and national press. And even Costing the Earth, which did a very balanced and nice programme a few weeks ago, could not resist in its last sentence talking about a nuclear dump, with the implication that we just chuck it in there. And it's not an engineered facility, which I find quite depressing. So we need to think about how to make this work. And so even in an area where the Moray poll, particularly locally at the district level, was hugely in favour, over 80%, we still didn't manage to get the process to move forwards. So what are my views? Okay, I've got a disclaimer at the top that these are not the views of the Quorum Committee, so these are my personal views. So I believe we have a responsibility, firstly, to minimise the risk to the public. There's a high hazard with having waste stored at the surface, not just the fact that you need to transfer that information through hundreds of thousands of generations before it's safe, but also it's far more vulnerable to things like climate change, tsunamis, terrorism, all the things that make you not want to have it at the surface. So in terms of just keeping the public safe, it makes far more sense not to have it at the surface. I also think we have an ethical and a moral responsibility. We used this energy, in fact, probably most of you, rather than me, some of it, but some of it, we use this energy and we should find a solution for it, and we should fund that solution. We shouldn't leave it as something for future generations to do. I also have a few thoughts about future power. I think we've a tough choice to make on future power. I'm not going to give any answers to it. I think there's a tough choice between dealing with the fact that we might have energy shortages if we don't invest substantially in nuclear. We can have nuclear, but we need to think about what we do with wastes. And we are it's pretty clear, look at the flooding this year, that there are issues associated with climate change. If we keep expanding our hydrocarbon production, then we just add to that problem. And I'm concerned at a policy that's predicated on carbon capture and storage when it's a technology that's entirely unproven. It's an industrial scale at the moment. So a few lessons learned. News reporters are not scientific experts, and simple statements make extremely good headlines, and the anti-campaign got far more press coverage because of that, I think. A safety case takes 10 to 20 years to build, looking at other countries. The arguments are very complex and technical and probably not that newsworthy because of it. And also the public can't weigh one expert argument against another. And that was really clear when you looked at the press coverage as well, that neither can the press. And they make no attempt to say whether it's one person saying something or the whole of a body of academia either, which doesn't help. And I think a good example of that is MMR. Despite the fact that one person did the MMR study and decided the vaccine wasn't safe, and since then tens of scientists have tried to repeat it and showed that they can't repeat the results, there are still many people that believe that the MMR vaccine is not safe. And I think that the same issue dogs this problem as well, in that the reporting of it is not helpful, and the arguments are complicated. So we somehow have to get over this hurdle, and if you look at international experience, it does show that public support is necessary to have success in all of this. So we need to have a think about how geological disposal siting processes could succeed. And I'm not going to answer it, but I'm going to raise one or two thoughts at the end here. And there was a new siting policy that's being developed now by the Department of Energy and Climate Change, and a white paper will hopefully come out later this year. There was a public consultation which ended in December 2013. Now, it's not for me to present any results for that, that's for the department to do, but I'm just going to raise some of the issues that very quickly that I think are key. First of all, one of the things that was consulted on, and one of the things that was very clear in the problems in Cumbria, was that there's a lot of concern about geology and geological suitability. And there is a question about whether some pre-screening of geology should go on before you have a volunteer, so that people aren't volunteering areas that other people think are unsuitable. So there is, I think, some problems with it. I can see some arguments for having some information, but I think we all need to bear in mind that actually there's extremely sparse data at any depth. So there are very few boreholes in the UK that go down to depths of 1 kilometre, very few. And mostly where they do, they're associated with the oil and gas industry, which means they're not in suitable locations. So for the most part, the data isn't there. And what you're actually relying on is geological models. So you're relying on somebody's interpretation, which means it's probably not accurate. So you could rule out and in areas, in fact, by screening on very little data. And I think that is a concern as well for public confidence. If you go to the public and say, we think this is a great area, and you drill your first hole and what you thought was there isn't, then that might be an issue for confidence in the whole process. So we need to be very careful about how we present geological data and the uncertainties that are in it, and possibly think about doing things like presenting the actual data and not the map, because the public's view of a geological map is like a road map, i.e. the roads are there. Whereas actually, when you look at a geological map, they're an interpretation of the data, and at these kinds of depths, there is very, very little data and sometimes none. So they really are an interpretation, they're a best guess, and that's not how the public sees them. We still need volunteers. So even if we screen the whole of the UK and say, right, this 60% here looks like it might be quite a good bet, or this 30%, you still need people to volunteer in those areas. And since we don't know what's at depth, we don't want necessarily wish to exclude areas where we might get people to volunteer, because if they're the only people that volunteer, it's worth a look. So we need to be a bit careful about how much we really screen out, because we still need volunteers. And to be honest, although the press likes to leap on geology, the focus shouldn't be geology, it should be safety. And I hope that I showed you in the different safety cases that actually in different geologies, the geology plays a variety of roles. So it's not all the same. So the design of a safety case is for the geology, and it's certainly true that some geologies it won't be possible to make safe, but there may be many that it is. So the focus should be on safety and demonstrating long-term safety and not the rocks. Okay, another issue is when do we need public support? Despite the fact that we had public support in the last region, we still didn't get a decision to participate. And I think some thought needs to go into a future process about when we should be making decisions. It's very interesting. The Corn Committee did a visit to Sweden last year, and one of the very interesting things was that in Sweden they didn't have a net. They were a volunteer community, but they didn't have some kind of vote early on like we have done. And what's interesting is that the local public confidence has steadily grown over 3 decades. And that's essentially because more and more information became available, the safety case got more detailed, and the public were allowed to raise issues as part of questioning that safety case, and the company had to respond to those issues and produce data to show that it was safe. So there's been an iterative process between regulators, public, and the company, which has meant that as they've answered all the questions, public confidence has grown, and now at the point of the licence application, it's at more than 80% locally. There's another question about who the decision-making body should be. The previous process that we have had failed to find a site, and that's despite the fact that we had substantial local support in a whole district. So there is some thoughts about who should be making the votes, and eventually, should we have these fixed decisions, I think, or should we wait until we have data to support things before we ask people to vote? And also, alongside that, there was a lot of negative press about having community benefits, but I think, so that's something that as a process moved on could be decided upon, but we need to think as well about who should receive them. Should it just be the area that's local to a site, or is it a much wider area? And there was discussion in Cumbria, at least, about this having a negative impact on tourism in the Lake District. Personally, I find that hard to believe when people still visit it with Sellafield there, which is considerably more notable on the skyline. So I don't see why it made any particular difference. Okay, and finally, how do we engage the public? And I think the big issue as well is the press. So we need to somehow raise the level of debate and make it an informed debate that thinks about, separates what we have to do with legacy waste, but also thinks about future energy needs. And for, at the very least, for legacy waste, the UK needs to deliver a site for public, to reduce public risk and deal with the energy that we have used. I'm just going to leave you with this thought. I searched the web. These photographs are all from the UK, and they are protests against the only form of energy I couldn't find protest groups against was geothermal. So we have to have a think about what our energy future might look like. That's me. Thank you very much.
Well, we have time for a few questions. Goodness me, we're going to start in the middle here. Mr. Arthur.
There's a roving mic somewhere.
Yes, roving mic is approaching roving mic.
Yes, John Arthur. Very nice presentation, thank you very much. You suggested that pre-screening might be useful. I did think that Professor Stiles of Keele had actually done some pre-screening work to exclude areas which might not be geologically suitable.
That's correct, but they're not based on whether they're geologically suitable. So there was in the Cumbria area, there was an exclusion screening, which could potentially be done everywhere, but it doesn't screen on whether suitability of the geology. So the exclusion criteria were based on the likelihood of future human intervention into the site. So they excluded areas that might in the future be deemed oil and gas resources, mineral reserves, and aquifers. So it was about not knowing where the site was in 10,000 years' time, and suddenly decided you wanted to exploit a resource and drilling through it. So not based on whether you could create a safety case for the geology.
Let us go back there. Thank you. Just to your right, sir.
Hello, my name is Barry Davis. I was a geological consultant before I retired. Some 15 or so years ago, I consulted for Fluor, who were making a proposal to the Atomic Energy Authority for disposal of radioactive waste. The proposal was to drill into salt domes in the southern North Sea, which were very well delineated, very well mapped, and drill holes and drop suitable containers down them that would last for many, many years. But because of objections from Greenpeace and various other agencies, I think the whole thing fell through. Can you explain whether such a proposal could be possible, viable, and if not, why not?
My understanding at the moment is that that would be difficult from a planning perspective because you would be outside so the Crown owns, I think it's 5 kilometres that surrounds the shore, but I think you would then be into international law when it comes to planning. So I think one of the issues with that would be getting permission to put your site there and into what's effectively international waters. But in terms of actual general feasibility, I mean, I guess I'm separating out what's politically feasible from what might be geologically feasible. I think geologically there's nothing wrong with salt domes, for sure. And I think WIP shows that, it's salt. I think there would be more transport and technical complications with site operation if you were doing it subsea, but it doesn't mean it couldn't be done. Yeah.
Very good. There's a gentleman over here. Let's try on this side.
Thank you, Mr. Chairman. My name is Robert Freer. There are several instances where the waste from one process in one generation becomes raw material for something else in the next 2 generations. Could you say a little bit more about Corem's view on recovering what you're going to put down in deep holes if somebody finds it technically possible to do so, use it again.
Okay, the current Quorum Committee hasn't looked at recoverability and retrievability of wastes. However, the previous Quorum Committee, as I understand it, which was before I was on it, but the previous Quorum Committee regarded it as not an issue because essentially because the technology is there to mine the wastes out anyway. So if you wish to mine them back out again, you could do. So the view was taken that a repository should be sealed so that it doesn't require long-term management, and that if you required it, we already have the technology to recover them even if you seal it.
Let us try over on the right here. Was there someone over that side? Yes, there we are. I thought I caught your eye. Hang on, wait for the roving mic. And there we go.
Yes, I think it's the disposal of nuclear waste in the past, because I mean I've been to go up to Dumfries and Galloway, and there's was a power station there called Chapel Cross, and I seem to remember that somebody told me, I don't know, is that they used to just sort of flush their nuclear waste out into the Solway Firth, mixing it with the raw sewage from the nearby towns in the process. And I was just thinking, you know, in the 50s and 60s when sort of nobody really known. And I think that legacy of sort of disposal straight into the sea without any sort of storage and so on, sort of still sort of the older generation is still sort of wary of that.
You're right that there was dumping at sea, and quite a few, I couldn't list them all, but quite a few nations, us and Russia, and a few other nations did dispose of it at sea until it was banned by international law for good reason, I think, basically. But you're right, that there was a period where there was a small amount of sea disposal, not of spent fuels or anything, but of some waste. Yeah.
Now, one more in the middle. Gentleman in the blue shirt. Hang on, wait for the mic. I know you're keen. Thank you.
Hello, thank you very much for your talk. I'm basically in favour of nuclear power if we can make safe decisions about it. I'm an architect, very interested in good low emission energy for our homes, and I think it's very important indeed, our future energy from nuclear, if it's safe enough. And it may not be the biggest pile at present, but it's most going to cause an effect on the future decisions about your disposal and future nuclear proposals. In the building industry, as an architect, I know that with the best intentions in the world, every builder makes cuts, corners. We have the Titanic was presumably made as safe as possible. I have a neighbour whose wife died because she was a child at Windscale. Her father was a fireman at Windscale. He died very quickly. She died about 40 years later. We know accidents happen. We know it was terribly badly designed. It was a new technology. Burying waste is a new technology too. May there not be, I fear, that there's a good reason. You also say 80% of people of the public were in favour, despite the place that it was unsuitable geologically, but then these 80% should not be the only reason you make a safe decision, because they're not scientists. They can't possibly weigh up all the science. I think there's very good reason to wonder how we can make an adequately safe. I mean, you are very confident in what you say about safety. I have less confidence.
Okay, well, there's a few things in there. I agree with you that it's not enough for a community to be in favour. You need to have a safety case that's pored over by regulators, that's extremely detailed and that demonstrates site safety. I agree, and I didn't say that the geology was unsuitable in Cumbria. I think we don't know if it would be possible to find suitable geology in those districts. We never got that far. So in terms of future, I think there you are determining safety. You are looking to the regulators, essentially. You're looking for strong regulation. We have a track record of strong regulation in recent years in the UK in the nuclear industry. There's a very strong safety culture. In fact, if you go when the Quorum Committee does meet with the public, probably the areas that are most in favour, well, in fact, certainly the areas that are most in favour of nuclear are, interestingly, those where nuclear power is, where the workforce is generally very strongly pro the companies involved. But I agree with you, you need extremely tight regulation, operational and constructional controls, and a very detailed safety case. And one of the ways of ensuring that is transparency and having the ability for people to raise issues during the development of the safety case and during R&D, and that the proponent has to respond to those issues. That's one of the ways of ensuring that the safety case is robust and well-founded. Is allowing people to raise those kind of things.
We have time for one more from the middle. The gentleman in the red pullover. There we go. Have to pick someone at the end.
I may be wrong about this, but I read a couple of years ago that Norway had embarked on geological storage, but having seen one of your earlier slides, my geography might have been wrong and it could have been Finland. But at the time, the suggestion was they'd be prepared to take waste from us, presumably at a price and depending on volume. So I wondered if you could comment on that.
I don't think there are any nations that are proposing to repatriate wastes. So I don't think there's anywhere that's proposing to do that, not that I know of. In fact, generally, even when you recycle, so for example, not absolutely everywhere, but in Europe, certainly, if you use, for example, contaminate radioactive metal recycling facilities to reduce waste volumes, the residue that's left, that's radioactive, that needs disposing of, that's left from that, so not the metal that can then go to market, but the bit that's left has to be repatriated back to the UK if we use the Swedish facility, for example.
Well, thank you. Thank you very much for a wonderful lecture and some very interesting questions. Let's celebrate in the normal way. And Professor Lunn does it all over again in a few hours' time.